Physics is the study of the world around us, asking some of the most profound questions in human history. How does the universe work? What holds matter together? And what is this strange force, gentle enough to make an apple fall, yet powerful enough to lock the moon in captive orbit? Our need to understand has inspired some of humankind's greatest discoveries, from unleashing the fearsome power of the atom, to uncovering the nature of light itself, to revealing the forces that hold our entire universe together. These are the greatest discoveries in physics. This curiosity that drives us to understand the world around us isn't new. In fact, it's been around, well, as long as we have. The ancient Greeks, for example, were the first to develop the idea that nature obeys a set of laws. This is a tremendous breakthrough. They gave us notions about how the universe works and about the way things move. Trouble was, most of these notions were dead wrong. That's because the laws of physics sometimes seem to defy common sense, like our first great discovery. For some 2,000 years, it was believed that heavier objects fall faster than lighter objects. This conventional bit of wisdom was based on observations made by the Greek philosopher Aristotle. And people believed him because it seemed like common sense. But in the 17th century, Galileo Galilei decided to test Aristotle's law. Legend has it that his test involved dropping balls of different masses from atop the Leaning Tower of Pisa. To see Galileo's experiment in action, I paid a visit to the NASA Glenn Research Center in Cleveland, Ohio, and met with Steve Simons, project manager for microgravity research. So this is the chamber.
Yes, this is the vacuum chamber. It goes 400 feet into the ground, and we have to pump all the air out of that so that we can get a good microgravity drop.
Now this goes back a long way, right, to Aristotle.
Aristotle, yes it does, where Aristotle thought that objects with different masses would fall at different rates.
Which seems reasonable.
It seemed very reasonable because all of the history that people had with objects of different masses fall at different rates. For example, if you have a feather and a ping pong ball, both fairly light objects, but they will fall at different rates.
Oh, yes.
To illustrate the difference between two objects that are roughly the same size and shape, but obviously very different masses, is a golf ball and a ping pong ball. And if we drop those, they do drop at the same rate.
Through Galileo's experiment, he found that a heavier object seems to fall faster than a lighter one because of air resistance. Air resistance slows a lighter object more than a heavier one.
The other way we do it is if we shield the experiment, which we can simulate with this leaf, from the effects of air, then they will drop at the same rate.
So what are we doing here?
Well, we're in our 5-second zero gravity facility, and we overcome the air resistance in this facility by pumping all of the air out of this huge vacuum tank. We've got an experiment set up here today to check out new fire extinguishers for possible use on the International Space Station. So we're going to see if helium is a better fire extinguisher than carbon dioxide. Anita, if you would, please.
So she's going to drop the big vehicle down.
And there it goes. 5 seconds, and it hits. And you can feel the floor shake when the drop vehicle hits. Hey, Bill, let me take you down to the bottom of the vacuum chamber. We can retrieve the experiment and see what happened.
What fun! Galileo's challenge to Aristotle's law was a turning point in science. It marked the beginning of testing the accepted laws of science through experimentation. And Galileo's experiments with falling bodies led to our earliest understanding of acceleration caused by gravity. A force, nearly 400 years later, we would overcome.
Well, in my left hand I have a feather. In my right hand a hammer. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct.
We owe our next great discovery to Sir Isaac Newton, who was born in England the same year that Galileo died. Legend has it that Newton was relaxing in an orchard one day when he saw an apple fall from a tree. This simple incident caused him to wonder why the apple had fallen to earth while the pale August moon continued to sail contentedly overhead. It was a eureka moment of insight for the young man. He realized that the same gravitational force acted on the apple and moon alike.
If you think about it, you get the feeling that all through this apple orchard, there's some force that's pulling the apples down. And what was really great about it was that he extended it beyond the apple orchard and all the way out to the moon. He realized that this force was everywhere, and this was something that nobody had really thought about before.
Newton reasoned that as the moon tries to travel in a straight line in space past the Earth's gravitational force pulls the moon towards it. This keeps the moon trapped in orbit around the Earth. But the moon pulls on the Earth too, with its own gravitational force. Newton had discovered what is called the law of universal gravitation. Universal because the relationship applies to all bodies in the cosmos, including apples, moons, and planets. When the gravitational force of a large body, like the moon, acts upon the Earth, big things can happen, such as the ebb and flow of the Earth's oceans.
The water in the ocean that's near the moon feels a greater pull than the water that's on the other side of the Earth, far from the moon. So it gets pulled out a little bit, and then as the Earth rotates, there's this kind of bulge in the water, and as the Earth rotates against it, it gets higher water and lower water.
Newton's recognition that all objects have their own gravitational force was a landmark discovery in science. But as our next discovery shows, he was far from finished. To many people, Sir Isaac Newton is physics, and it's largely because of a series of 3 books he wrote which contain Newton's second great discovery, the laws of motion. The laws explain the movement of all physical objects. To help understand the 3 laws of motion, consider ice hockey.
It's simple enough. You hit a hockey puck and it just keeps sliding off across the ice. You can see that on a frictionless surface, it'll just pretty much keep going indefinitely. When you hit your stick against the puck, it accelerates it, and the nature of that acceleration that gets it from being standing still up to speed is explained by the second law, or rather, you can calculate it using the second law. The third law says that when you hit the puck with the stick gets the force equal and opposite to the puck, or to put it another way, if one of the hockey players punches the other one in the face, he's as likely to break his knuckles as the other guy's jaw.
Newton's laws of motion were a bold insight into the mechanics of how the universe works. They established the foundation of what is now known as classical physics. This is the science of thermodynamics in action. The science of heat transformed into mechanical energy. The power-driven machinery of the Industrial Revolution depended on it.
Heat energy can be turned into the energy of motion, such as by turning a crank or a piston or a turbine to be used to pump water, to turn a loom to make fabric, to move a boat through the water, to move a train down rails. Now, it's desirable to get more oomph for your dollar, to get more work done for the amount of fuel you're going to use. And so people began to study how heat engines, how steam engines really work.
Among those who studied it was a German scientist named Rudolf Clausius, who in 1865 formulated our next great discovery, what became known as the second law of thermodynamics. The law states that in any energy exchange, such as heating the water in a steam engine boiler, some energy is always wasted. Clausius coined the word entropy to explain why the efficiency of a steam engine is limited, because some of its energy will always be lost in the process of converting it to mechanical work. It was a momentous insight, one that changed our understanding of how energy works.
There's no heat engine that is 100% efficient. When a car is moving along, how much of the energy implicit in the gasoline that you put into a car actually gets used to move the car and you in it? Only about 20%. Where does the rest of it go? It goes to heating up the pavement on the road, heating up the tires. The cylinders in the engine block get hotter. They wear out, parts corrode. It's sobering to think how wasteful these processes are.
While the second law of thermodynamics was a driving force behind the Industrial Revolution, our next great discovery powered the world into the modern age. It's one of the great engineering feats of the 20th century, the Hoover Dam. 726 feet high, weighing 6.6 million tons. The dam's 17 generators produce nearly 3 million horsepower of electricity. Electricity created using a magnetic field. Scientists had figured out how to create magnetism with electricity by running an electric current through loops of wire. The result is an electromagnet. Turn on the electric current, and a magnetic field is created. Turn off the current, and the magnetic field disappears. In 1831, a bookbinder with an interest in electricity named Michael Faraday was first able to reverse the process using a moving magnetic field to create electricity. An electric generator, in its most basic form, is just a coil of wire between the poles of a magnet. Michael Faraday discovered that when the magnet and the wire move near each other, an electric current passes through the wire. Every electrical generator works on this simple principle. Faraday kept somewhat cryptic notes on his experiments, but years later they proved invaluable to a physicist named James Clerk Maxwell, who used them to contribute to our understanding of how electromagnetism works. To find out more about this discovery, I paid a visit to the Museum of Science in Boston.
Bill Nye, this is great. So what is this device?
Well, this is a generator, and we use it here at the museum to talk about lightning and lightning safety, and a little bit of what you were just mentioning, that sort of connection between electricity and magnetism. We've got this demonstration, this sort of giant bird cage, and we can use that to show how electricity and magnetism are sort of interrelated. Would you like to try it?
Well, yes, of course.
Well,
one test is worth 1,000 expert opinions.
After you.
One of the things Maxwell helped us understand is how electromagnetic fields are distributed on a conducting surface, like the metal this cage is made of.
And now, if you want, when I start to make some of the sparks, if you put your finger on the inside of that bar, you should be okay. If you want to give it a try.
If Maxwell was right, the enormous 1.5 million volts of electricity created by these generators will distribute itself nicely around the outside of the cage and not be able to penetrate the inside. Right now, I'm hoping James Clerk Maxwell was right.
You ready?
Yeah.
Well, go ahead, put your finger up there, and we'll give it a try. Here we go.
It is spectacular. So, what's happening? The electricity is hitting the cage, and that's creating a magnetic field?
That lightning bolt is a current of electricity. It strikes the cage, and that turns the entire cage into sort of a giant magnet. The magnet, in turn, makes another electric field. And that electric field around the outside of the cage pushes all the electrical current to the very outermost surface.
Yeah, it's amazing. Well, thank you very much.
Well, thanks for coming.
I'll never forget that. That is just spectacular. I'm fine. If you want to know what the world would be like without the work of Faraday and Maxwell, imagine a world with no electricity. There'd be no radios, no television, no cell phones, no satellites, no modern communication of any kind, no computers. Think of being in the 19th century. That's where you'd be. Now, what Faraday and Maxwell couldn't know was that their discoveries would inspire a young man who would go on to unlock the secrets of light and its connection to a fearsome power in the universe. In 1905, the scientific world was turned upside down by our next great discovery, one of several revolutionary theories put forth by a young, unknown scientist working in a patent office in Bern, Switzerland. His name? Albert Einstein.
Believe it or not,
To find out about Einstein and his discovery, I paid a visit to Michio Kaku, a physicist at the City University of New York.
Einstein once said that all ideas should be presented to children, and if children can't understand it, the theory is worthless. When he was a child, he read a children's book. Electricity was just coming in at that turn of the century, and people were fascinated by telegraph wires. And there's one book by Mr. Bernstein that says, imagine yourself racing alongside a telegraph signal inside a wire. That's where we think, historically speaking, Einstein got his earth-shattering idea, from a children's book.
When Einstein was a teenager, he was inspired by his memory of the children's book to imagine what would happen if he was riding on a beam of light. He pondered that idea for the next 10 years and began thinking about light, time, and space. He realized that Newton's theory that space and time were fixed and absolute did not apply as you approach the speed of light. From this insight, he formulated what he called the special theory of relativity.
In Newton's world, space and time were always separated. If it's 10 o'clock on the Earth, it's 10 o'clock on Venus, it's 10 o'clock on Jupiter, it's 10 o'clock throughout the universe. Time was like an arrow. Once you fired it, it never came back, never deviated. Einstein comes along and says, not so fast. Time is like a river that meanders around stars and speeds up and slows down. Now, of course, if space and time can change, that changes everything. Everything we know about atoms, everything we know about our bodies in the universe changes once time and space also change.
Einstein demonstrated his theory with what he called thought experiments.
The most famous thought experiment is the twin paradox. You get two twins on the Earth, you put one in a rocket ship, send that person off, and of course, that person accelerating near to the speed of light, his time slows down. And so when the two people come together, the twin in the rocket ship is younger than the twin on the Earth. Time beats at different rates throughout the universe.
Depending on what?
Yeah, depending on your velocity. The faster you move, the slower time beats.
Now, we have, in a very small way, done this experiment with orbiting astronauts, right?
That's right. If you have astronauts and send them into outer space, time beats slower on the space station. Time beats slower. That affects all satellites. Look at the GPS satellite. You realize that it's so accurate, you can locate your position to within about, 20 feet of the planet Earth.
You can tell which side of the street you're on.
That's right. So the satellite going around the Earth is going very fast, 18,000 miles per hour. Therefore, you have to include relativistic effects. Now, if the two clocks are out of synchronization, if the clock in outer space runs slower than the clock on the Earth, the GPS system is totally out of whack.
A few months after publishing his special theory of relativity, Einstein followed it up with our next great discovery, the most famous equation ever written.
E equals mc squared, maybe the most famous equation known. Where did it come from?
Einstein used relativity to show that as you approach light speed, bizarre distortions take place. Time beats slower. Space contracts and you get heavier. The faster you move, the heavier you get. Now think about that. The energy of motion has turned into making you heavier. M came from velocity, energy. Here's how he did it. He imagined a flashlight shooting a light beam. He knew exactly how much energy came out of the flashlight. But the flashlight he showed weighs less. The flashlight weighs less by emitting a beam of light. Therefore, the E of light came from the M of the flashlight. And the ratio is c squared. That's how it's done.
The equation also hinted at the enormous amount of energy contained in even a small quantity of matter.
Suppose I throw a baseball at you, okay, and you catch it. The faster I throw it, the more energy it's got. Now, what about when it's standing still? Well, when Einstein goes through his equations, he finds even when it's standing still, there's a lot of energy in it. And in fact, when you do the equations, it's got an enormous amount of energy in it.
Einstein's discovery was a gigantic leap for science, our first real glimpse into the power of the atom. While scientists were still trying to digest it, our next great discovery sent science reeling yet again.
A quantum leap is the very smallest leap possible in nature, but it's proven to be an enormous step in thought. Subatomic particles, like electrons, are able to move from one point to another without ever occupying any of the space in between. An impossibility in our everyday world, but commonplace in the realm of the atom.
In the subatomic world, atoms and their constituent parts play by a completely different set of rules from larger bodies of matter. A German scientist named Max Planck described these new rules in what he called quantum theory. And it's our next great discovery.
The quantum theory emerges around 1900 because there was a crisis in physics of monumental proportions.
A crisis.
A crisis. New phenomena were being discovered that violated Newton's laws. Madame Curie, for example, refined something called radium. Radium had this magical property of glowing in the dark. Energy was coming out of nothing. Particles were coming out of nothing. That violated the conservation of energy. Energy was coming from nowhere. Around 1900, people thought that energy was continuous, that you could cut electricity, magnetism, you can cut it into finer pieces without end. And yet around 1900, Max Planck, the great physicist, had the audacity to say that energy occurs in packets called quanta.
And why did he say that?
Because if you assume that light comes in these packets, then you could explain all the different kinds of phenomenon that we were seeing, that at the fundamental level, at the level of the atom, there was a quantum effect, that energy was occurring in packets. This also meant, by the way, that matter has wave-like properties.
And this is what we call quantum mechanics?
That's right. Now, that's not the way the universe was supposed to be constructed. The atom was like a bowling ball. How can a bowling ball have wave-like properties? Well, in 1925, Erwin Schrödinger, an Austrian physicist, finally writes down the wave equation governing the electron. This is one of the greatest achievements of the human intellect. All of a sudden, we can now peer into the atom itself.
And so we're talking about atoms are waves, atoms are particles, but there's an uncertainty associated with them, right?
That's right. Then a few years later, Max Born, a colleague of Albert Einstein, made the fateful step. The question was, if matter is a wave, then what is waving? Max Born said, what is waving is the probability of locating it at any given point. We sometimes give our graduate students the problem. Calculate the probability that you will dissolve and you will rematerialize on the other side of a brick wall. Now that's absurd. How can you wake up in the morning and wind up on Mars? How can you go to bed and wind up on Jupiter? That's crazy. And yet you can calculate the probability of that happening.
It's probably low.
It's very low. You would have to wait longer than the lifetime of the universe. But for electrons, it happens all the time. That's what we call electronics. All the modern marvels of the electronic age and laser beams and microchips ultimately come down to the fact that electrons, you don't know where they are, they can be two places at the same time. How can that be? Two places at the same time? Because you don't know where objects really are. This caused so much problems that even Einstein finally broke with the quantum theory. And he said that I cannot believe that God plays dice with the universe.
With all of its weirdness and built-in uncertainty, quantum theory remains the best model of the subatomic world we have.
The ancients asked a fundamental question. What is the universe made out of? They thought it was earth, air, fire, water. But if that's what the world is made out of, then what is light? You can't put it in a box, you can't shake it, you can't touch it, it's ephemeral, yet it's everywhere. Light is everywhere and nowhere. Everyone experiences the epiphany of light. But the question is, what is it? And that has dogged physics for thousands of years.
Dogged physics? Doesn't that just make your day, though? Isn't that a reason to come to the office?
That's right. That's why some of the greatest minds, going back to Isaac Newton, made the first definitive studies on the nature of light. Newton, for example, took white light from the sun, shone it through a prism, and showed that all the colors of the rainbow would come out of white light, showing that white light is really a composite, a sum of red, orange, yellow, blue light.
Didn't he also recombine it?
That's right. He could also show that Roy G. Biv, red, orange, yellow, the violet, could be recombined to create white light. So Newton thought that light was in some sense particulate, little tiny corpuscles, as he called it, made up the stream called light. So we had the first theory of light, the fact that light is based out of particles. But however, there was an alternative theory, a rival theory to Newton's theory that said that light was a wave. And there was a guy named Young who many years ago was able to show that light had wave-like properties. Think of surfing, for example. Every surfer knows that you could ride on an ocean wave, but if a second ocean wave comes at you from another angle, the two waves interfere, giving you an interference pattern. And then, of course, if you're not careful, you wipe out. Mm-hmm. Well, Young showed this with light. He was able to get light, shine it through a small little pinhole, get another pinhole of light, and have these two waves collide with each other, and there it was, a beautiful interference pattern. So we now had two rival theories of light, the Newton corpuscular particular theory of light, and Young's and others' wave-like theory of light.
Now, Einstein took this the next step.
What Einstein said, and this is the genius of Einstein, he said, perhaps both are right. Perhaps Newton showed us that light has particle properties, and that Young showed that light has wave-like properties, and the two are different manifestations of the same thing. Think of like looking at an elephant. You touch the trunk, you think the elephant is a snake. You touch the legs, you think the elephant is a tree. And yet the elephant is a merger of all these qualities. So Einstein introduced the concept of duality, particle and wave-like duality.
What are we looking at?
Here, we're looking at a helium-neon gas laser. It emits a milliwatt of energy, and it demonstrates that light has both particulate and wave-like nature. Look at this. It really does look like light consists of particles. It's a collimated beam, very, very coherent, meaning that all the waves are vibrating in unison.
If there were waves.
If there were waves. Now it goes through this double slit. And as it goes through the slit, it starts to interfere with itself. Waves start to crisscross other waves to create this pattern. So as we see here, the wave starts to disperse. Now, if waves were nothing but photons, individual particles, this would be a simple red dot. But it's not a red dot. It looks like a wave-like pattern. Mm-hmm. That demonstrates in one experiment both the particle and wave-like nature of light, the duality of light.
It took the combined efforts of three geniuses across 3 centuries to help us understand light as we know it today. Without them, we may as well be living in the Dark Ages. The atom, so small it's hard to imagine. 72 quintillion of them fit into a single grain of sand. Finding out what an atom was made of led to our next great discovery. To get the story, I went to Fermilab outside Chicago and met with physicist John Wormersley.
Even 100 years ago, people knew how big the atom was, and they thought that electrons and protons would be spread pretty much uniformly throughout the atom. And they called this the plum pudding model because they thought of the electrons like raisins in a fruitcake spread throughout the inside of the fruitcake.
In the early 1900s, physicist Ernest Rutherford conducted an experiment to further explore the structure of the atom. He shot radioactive alpha particles at a sheet of gold foil.
And he wanted to see what would happen when the alpha particles hit the gold. He didn't expect very much would happen. He thought most of the alpha particles would carry straight on through without being deflected, without being bent through any large angle. But what happened? Well, he found something completely different. He said it was as surprising as if you shot a 15-inch artillery shell at a piece of tissue paper and had the artillery shell bounce back at you. Some of these alpha particles bounce straight back off the gold foil. So the only way this could happen is if inside the atom is a very small, dense concentration of matter. It's not spread out like the plum pudding. And Rutherford called this small, dense concentration the nucleus. What we're doing here at Fermilab is the descendant of that experiment. We take a beam of protons and collide it with a beam of antiprotons to see what the protons are made of.
Thanks to Rutherford's discovery, scientists now knew that the structure of the atom included protons, electrons, and a nucleus. But it was up to James Chadwick, a student of Rutherford's, to complete the picture with the discovery of the neutron.
So we're standing now inside the D0 detector, which is one of the particle detectors in the Fermilab Collider. That pipe there is where the protons and antiprotons actually circulate. And they come into collision a few feet to your right, and all of this instrumentation around it is the equipment that we use to detect the results of those collisions, which kind of takes us back to the history of the neutron. Chadwick was able to carry out an experiment that showed that what the nucleus was made of was protons and neutrons. And what Chadwick used was a clever detection technique, which is what we're standing in the middle of to do that. Except he didn't build a big piece of apparatus like this. He used paraffin wax.
Like from a candle.
Like from a candle. And what Chadwick did was to use this wax to intercept those particles that came out of the radioactive process. And then suddenly all the pieces fit into place.
The discovery of the neutron changed history. In 1939, a group of scientists led by physicist Enrico Fermi used the neutron as a bullet to split the atom, giving birth to the nuclear age. Fermilab is home to one of the largest particle accelerators in the world. A 4.5-mile-long underground ring where subatomic particles are accelerated to nearly the speed of light and then smashed into each other. To accomplish this feat requires the help of our next great discovery, the superconductor.
Who discovered superconductivity? Why was it such a big deal?
Well, it was way back before the First World War, I think 1909, something like that. A Dutch physicist called Heike Kamerlingh-Onnes was the first guy to figure out how to turn helium from a gas into a liquid. And once he'd figured out how to do that, he could use liquid helium as a refrigerator fluid to make other materials very cold. And he wanted to study the properties of materials at very low temperatures. And one of the things that people were interested in at that time is how does the electrical resistance of a metal, for example, depend on temperature? Does it rise? Maybe it gets very resistive at low temperatures. That was one idea. So Onnes took a sample of mercury, which he could make very pure, and he put it in an apparatus kind of like this one. He just dipped it in liquid helium in a refrigerator vessel and measured its electrical resistance as he lowered the temperature. And what he found was that as you lowered the temperature, the resistance went down fairly smoothly, and then suddenly, when he got to 4.2 degrees above absolute zero, the resistance dropped to nothing, absolutely to zero. This mercury would conduct electricity with no resistance, without losing any energy, without dissipating the current at all. And that was what he called superconductivity. So to see some superconductors at work, Bill, we're going down into this tunnel about 30 feet below the prairie in Illinois. And this is the Fermilab Accelerator tunnel. In this tunnel we have a large ring of superconducting magnets which we use to accelerate and contain protons and antiprotons that we're using to study the properties of matter. It's a big tunnel, 4 miles long, so we've arranged a little transportation for you.
Ah, it's lovely.
Beautiful, isn't it?
It is. So we're using superconductors here.
Superconductors allow an electric current to flow without losing any energy. And we can use them to generate a strong magnetic field, and that's what we're doing here. These are magnets, so we use the magnets to keep the protons and antiprotons circulating in the tevatron, going round and round this big ring. They travel at close to the speed of light. It's 186,000 miles per second faster than we're going. Kind of exhilarating to do that speed in this car.
I would feel massive, though.
That's right.
The particle accelerator at Fermilab requires enormous power. It costs more than $1 million worth of electricity every month to refrigerate the lab superconductors to minus 455 degrees Fahrenheit, the point where electricity flows with zero resistance. The technical challenge now is to find superconductors that work at much higher temperatures at a much lower cost.
Starting back in the 1980s, a couple of researchers at IBM in Switzerland found a class of materials that superconductors about 100 degrees warmer in temperature than this kind of device. Now 100 degrees above absolute zero is still not the kind of temperatures that you have in your refrigerator. Of course, the holy grail is to find a material that's a superconductor at room temperature, because that kind of thing, if it could be made into useful electrical conductors, would really revolutionize the world. All of the things in your house that use electric current or that use electric motors would be changed and made much more efficient by that.
Our next discovery takes us on the quest to find the smallest pieces of matter in the universe. First, the electron was discovered, then the proton, and finally, the neutron. Science now had a new model of the atom, the tiny building blocks that make up all matter. And once accelerators were developed that could slam subatomic particles together at nearly the speed of light, dozens of new particles broke away in the process and were discovered. So many, in fact, physicists began to refer to them as the particle zoo.
In the late 40s and early 50s, when the discovery of so-called strange particles began, I got very interested in that. But it was an offbeat field. One wasn't encouraged to work on that.
American physicist Murray Gell-Mann began to see patterns in the bewildering array of all the new members of the particle zoo. He used common characteristics to divide particles into different families. In the process, he isolated the smallest components of the atom's nucleus, the very pieces that protons and neutrons are built from.
As a theoretician, I couldn't, I suppose, really discover new things, but I could propose them. And if they turned out to be right, you could call it a discovery in a sense. What I did was to propose that the neutron and proton were not elementary, as everybody thought, but were composed instead of smaller particles called quarks with some very bizarre properties.
Gell-Mann's quarks did for subatomic particles what the periodic table did for the chemical elements, and in 1969 he was awarded the Nobel Prize for Physics. His classification of the tiniest bits of matter brought order to the chaos of the particle zoo.
I thought that the sound, quark, was a good sound for these fundamental constituents. It sounds like a good name for the fundamental constituents of neutrons and protons and mesons. Quark. But I didn't know how to spell it. I thought maybe K-W-O-R-K. But then, perusing James Joyce's Finnegan's Wake, as I do once in a while, I noticed the line, 3 quarks for Muster Mark. And I thought, 3? After all, that's a very important number for quarks. And maybe I should spell it Q-U-A-R-K.
While Gell-Mann believed quarks to be real, he never expected anyone to find one.
Some of the earliest evidence that the quark idea was correct came from experiments by friends of mine at the Stanford Linear Accelerator, in which electrons were scattered off protons. And essentially, what they were doing was taking an electron microscope picture of the proton. And sure enough, there were the 3 quarks.
Our search for answers to the questions about the universe around us have taken us from the submicroscopic scale of atoms and quarks to the farthest reaches of the galaxy and beyond. Our last greatest discovery is actually the result of centuries of effort by countless men and women of science. Since the discoveries of Isaac Newton and Michael Faraday, scientists believe there were but 2 basic forces of nature. But in the 20th century, scientists discovered there were 2 more at work, what are known as nuclear forces, giving us a total of 4 fundamental forces of nature.
Each one acts over a different range. We have gravity, which keeps us on the Earth. Without gravity, by the way, we'd be flying at 1,000 miles per hour into outer space. That's what keeps us on the floor.
That would be surprising.
That would really ruin your day.
It would change, and baseball would be hard.
Yeah, right. Plus, you'd suffocate in outer space.
Oh, yeah, well, there's a couple issues. Yeah, okay.
Then we have the electromagnetic force, light, which illuminates the world, radio, television, all of that, the electromagnetic force. Then we have the 2 nuclear forces that only operate over a very short range. We have the strong nuclear force that holds the nucleus together, and the weak nuclear force gives us radioactive decay, and that actually heats up the center of the Earth. That's why the center of the Earth is still hot after so many billion years. That's the energy of volcanoes, the energy of earthquakes, the energy of plate tectonics is the weak force as manifested through heat.
How do you go about detecting the weak force? How do you know it's there?
We know it's there because we have Geiger counters. These particles that come racing out of the atom rip apart other atoms, and it causes a slight electrical charge. You can measure that charge, and it causes a click inside a Geiger counter.
How do you detect the strong nuclear force?
Well, the strong nuclear force is more difficult because it's what holds the atoms together. For that, we need atom smashers. For that, we have to smash particles and blow them to smithereens. Someone once compared this to trying to figure out how a piano works by throwing it down a stairwell and listening for all the tinkling sounds as the piano disintegrates going down the stairs. That's how we do it. We smash atoms apart.
You got your gravity, you got your electromagnetism, you got a weak force, you got a strong force. What's next?
Well, we now know that the quantum forces can be summarized as something called the Standard Model. It is perhaps the ugliest theory known to science, but it's very successful at the subatomic level. I like to think of it as getting Scotch tape and Scotch taping an aardvark to a shark to a giraffe and calling this horrible animal nature's finest product of evolution. This is supposed to be the ultimate theory, the Standard Model, and yet it's so ugly. Then we have gravity, beautiful, gorgeous, supreme, based on curved surfaces. You cry. Physicists literally cry when they see Einstein's equation. Well, obviously, the 2 have to come together. That's called the theory of everything. The theory that would unite all 4 forces into a single superforce that existed at the beginning of time.
We don't know if we'll ever find a superforce that includes the 4 fundamental forces of nature. We don't know if we'll ever be able to write a physics theory of everything. But this much is certain. Each discovery leads to more exploration, and we humans are a curious species with a drive to understand, explore, and discover.